Hey, everybody. So we're going to do some more with L'Hopital's rule. Last time we looked at limits where you have the indeterminate form 0 over 0, right? We don't know what that means. It could mean just about anything. Now we've got another case where we have the infinity over infinity result from a limit. So let me write out the rule. We'll talk for a moment about intuition and then mostly just do some examples. So suppose we have functions f and g are differentiable functions over an interval containing a. All right, so a is a real number, except possibly at a, right? So maybe a is at a corner or something like that. Further, suppose that the limit as x goes to a of f of x is equal to plus or minus infinity, and the limit as as x goes to a of g of x is plus or minus infinity, right? So it's going to be one or the other of those, right? I'm just pointing out with the plus or minus. The sign on the infinity doesn't matter. What's important is that we're getting something infinite for both of them. If both of them have infinite limits, in other words, their limits don't exist, but they grow increasingly large or small, or large negative. If that's true, then the limit as x goes to a of their quotient is equal to the limit as x goes to a of the quotient of their derivatives. Okay, assuming this limit, the limit on the right exists or is itself an infinite limit, right? We can also replace, it's true if a is replaced with one-sided limits, so coming from the top or the bottom, or positive or negative infinity. So we can take a limit out to infinity that has infinities in it and use L'Hopital's rule. Okay, so this is great. This gives us another set of indeterminate forms where we can use this. So I'll just say for a minute a little bit of intuition. The idea here is that if both of these are heading off towards infinity, f and g, right? Let's say we pick a point to start watching them. So let's say this is an infinite limit. The limit as x goes to infinity of f over g. If I look out over at x equals 1,000,000, and the value of f is 10 times bigger than the value of g, but g is growing at a rate twice as fast as f, eventually g will overcome f. It'll catch up because it's moving twice as fast. And eventually it will be basically twice as large, right? So even though f might have started out 1,000,000,000 times bigger, infinity is a long way away, right? It's an infinite amount away. All those doublings that g does, every time we move forward by one value of x, g gets twice as big. Eventually it's gone so many times twice as big as f, that bit that it was falling behind, that million it was behind in the beginning, pales in comparison to the 2 trillion it's ahead now, or 2 trillion, right? And so that rate is what really matters, right? Same thing if we're approaching a and both functions are shooting off towards infinity. The rate at which they're going is what really matters, because any differences in the values of where they start, right? If we pick a point where we're watching how big they are at this moment, it doesn't matter if one's bigger than the other. What matters is the rate, because we just keep going, and eventually that rate, the faster one will overcome, and that difference will become negligible, right? If two functions are different by 1,000, right? Let's say one is at 0 and one is at 1,000, but they're both, the smaller one grows twice as fast. You know, by the time we get out 1,000,000 units away, that one's 2 million and the other one's 1,000,001. That extra 100 it had in the beginning, or 1,000 or whatever I said, pales in comparison to the million we've got now, or the billion much later, and so on and so on. So it's the rate that matters. What's most important, though, is that we know how to use this right now, and the intuition can be built over time. So let's do a couple of examples. Let's look at the limit as x goes to infinity of e to the x over x, right? So first of all, we need to confirm, right, that the limit as x goes to infinity of e to the x, we know this one. This is one of our, we know the graph of this function, right? If we keep taking e to higher and higher powers, it just keeps growing larger and we have an infinite limit. And the same thing, what happens to x, right? This is kind of asking a silly question. What happens to x as x goes to infinity? Well, it goes to infinity. So these two limits are infinite. So L'Hopital's rule applies. Again, I like to make a little mark for myself. This is non-standard notation. As far as I know, maybe somebody showed it to me once and now I've been using it, but I don't remember ever seeing it anyway. So don't expect people to understand if you use it. But I'm using it just to tell myself what happens here. If I ever come back to look at this work, I'll understand what I did. I'm applying L'Hopital's rule. And so we take the derivative of the numerator, e to the x as its own derivative, and we take the derivative of the denominator, right? And the derivative of x is just 1. Remember, we're not doing the quotient rule, right? This is not a derivative. We're not taking the derivative of this. We're saying that the ratio in the limit, the ratio of the functions is the same as the ratio of the derivatives of the functions. We're not taking the derivative of this quotient of functions. And now we have just the limit as x goes to infinity of e to the x, which is infinite. So this limit doesn't exist. This function e to the x over x, even though they're both getting very, very large, e to the x gets large much faster. Exponentials always beat polynomials. Even if that x had a 10th degree on it, let's show that. If we had the limit as x goes to infinity of e to the x over x, what's due to the 5th, just to not make this unreasonable. Both of these have infinite limits, and so we apply L'Hopital's rule, and something interesting happens. Oops, not to the 5th, to the x. We get 5x to the 4th. Well, that still has an infinite limit, right? But I can just apply L'Hopital's rule again because we have infinity over infinity in the limit. L'Hopital's rule applies. I can get the limit as x goes to infinity of e to the x. I take the derivative of the bottom. I bring that 4 down. So now I've got 5 times 4, e to the 3rd. That's not e to the 3rd, x to the 3rd. Again, this is an infinite limit in the numerator and the denominator. We just keep doing this. Right? We do it a couple more times. The 3 pops down, the 2 pops down, and we've just got an x, and then we take its derivative and it's 1. And so by the end, what we'll have, applying L'Hopital's rule over and over and over again, that e to the x is never changing. We'll end up with 5 factorial in the denominator. Right? The cubic root or the cubic power comes down, then the square power, and then the 1 comes down, and the x disappears, just like what happened up here. We're just left with the 1. And that's just a number. And e to the x grows much faster than just a number, and we get infinity again, right? And so you could imagine I can do this for, a power of 50. It doesn't matter how big the polynomial is, an exponential will win, right? And the logic is, this limit we now see is infinity, which means that this limit by L'Hopital's rule, or well, one of the ones in the dot, has that same limit. And that means the one before it has the same limit. And that means this one has the same limit. And this one has the same limit. And so the one we originally wanted has that limit. And so we follow this chain backwards, right? If A equals B equals C equals D equals E equals F, it must be the case that A is equal to F. All right, let's do another example. Let's look at the limit as x goes to infinity of the natural log of x over the square root of x, x to the 1/2. Right? Well, natural log of x, that's another one we looked at a couple of videos ago. That goes to infinity, and then x to the 1/2 is also going to go to infinity. So we have infinity over infinity again. So L'Hopital's rule applies. Oops. So I'll take derivatives. I get the limit as x goes to infinity of 1 over, sorry, just a little nicer, 1 over x over, this will be 1/2 x to the negative 1/2, or 1 over 2x to the 1/2. Okay. This is a pretty ugly fraction, so let's do a little bit of algebra before we even think about limits. So really, this is going to be 1 over x times 2x to the 1/2 over 1, which is the limit as x goes to infinity of 2 over x to the 1/2, right? The 1/2 and the x down there cancel 1/2 a factor of x. And so 2 over x to the 1/2, that x to the 1/2 in the denominator grows and grows and grows and grows and grows, making the fraction shrink increasingly close to 0. And so this derivative is 0, or this limit is 0, right? So this is a good example where we have these cases where up above we had infinity over infinity as our original limit, our indeterminate form, and the overall limit turned out to be infinity. And here we have another example where we have an infinity over infinity result, an indeterminate form, and the actual limit is 0. And so it just illustrates to us that we can't tell anything from these forms, right? We've now seen both directions. Okay, let's take a look at another one. Let's do one more example, okay? Let's take the limit as x goes to infinity of the natural log of x squared over x, right? So we compared the exponential to polynomial in our first examples and saw that the exponential one. Here we compared natural log to a power of x to the 1/2, and we saw that the power of x to the 1/2 kind of won, right? It was making the fraction smaller. Now we've squared the natural log. Let's see what happens here. Again, we have two infinite limits, right? The x in the denominator and the natural log of x, even though squaring it only makes it larger for large numbers of x. So we've got infinity over infinity. We apply L'Hopital's rule. In the numerator, I take that denominator, or take that derivative, and I have to use the chain rule. So I get 2 natural log of x times 1 over x. In the denominator, I'm just getting 1. I'm going to rewrite this. This will be 2 natural log of x over x. Here I have infinity over infinity again. In our limit, right? Natural log goes to infinity, x goes to infinity. So I can apply L'Hopital's rule again. So now I've got the derivative in the numerator is 2 over x. The denominator is just 1. So now we see that this numerator, as x goes to infinity, is the alpha fraction that's going to 0. We end up with 0 over 1, and that limit is 0. And so the x wins. So exponentials will beat polynomials. I haven't shown you explicitly, but it turns out the reverse is true here, that natural log will always lose to polynomials, right? So exponentials grow incredibly fast, Polynomials kind of fit next, and then natural logs grow slower, or all logarithms really. Right, so this comparison is right. I'm setting them up in these fractions, so they're fighting each other. The top is trying to make it big, the bottom's trying to make it small. If my limit ends up being 0, the denominator is winning. If my limit ends up being infinite, the numerator is winning. Later, we can do some examples where we end up with a number, and it's sort of like they met in the middle, right? Okay, that's it for this one. We'll look in a later video at some other kinds of indeterminate forms, but the 0 over 0 case and the infinity over infinity case are really the big ones. Those are what L'Hopital's rule is for. The other ones that we'll come to, you get something different and you manipulate it so you get one of those cases. And so those are the ones we really have to work with. But we'll see that in the next one. Thanks, everybody.